Hello everyone, this time we'll be working on 2021 free response question number 1. This problem is a combination of ideal gas law, redox reaction, and acidity, which is analogous to what we found in 2023 free response problem number 5. So let's have a good understanding of this problem. First, we are given a equilibrium equation of a weak acid. Here we have formic acid. Formic acid is a common name. The IUPAC name is methanoic acid. And this one is dissolved in water. This one is a weak acid. And remember that those carboxyl acid portion is always weak acid, and this hydrogen is partially ionizing. And it'll be proton transfer will be occurring to water. Water will be accepting. Water is a weak base in this case. And it'll be forming conjugate base. So let me write here. So then this is an acid. And water is functioning as a base in this case. Water can be functioning as acid or base depending upon its solute. And becoming conjugate base and conjugate acid of water. That's hydronium ion. Ka value is 1.8 times 10 to negative 4. Look at this value. It is much smaller than 4 orders smaller than 1, which is an indication that this is a weak acid. Actually, all the carboxylic acid, they are weak acids. And let's look at number 1. Write the expression for the equilibrium constant, this acid dissociation constant K sub A for the reaction. Ka is defined like this way. Ka is equilibrium constant. So the product concentration molarity, let me write it bracket right there. The conjugate base, this methanoate ion, and multiplied by the conjugate base, conjugate acid, hydronium ion concentration over the acid concentration, methanoic acid. And remember, water is, in this case, is solvent. Solvent, the activity is 1. Rigorously speaking, the equilibrium constant is defined based upon the activity, and activities of solvent is 1. So solvent is not written, is not appearing in the expression of Ka. And remember, this ratio is always determined in any stage. And then, so we need to represent this one is at equilibrium. Let's put a vertical line. Let's write EQ, meaning this is at equilibrium. And here, the diagram on the right hand side is, I brought this one from the previous one. I see only a small portion of acid is deprotonated, forming hydronium ion. Majority of the molecules will be intact. The monoprotic acid, which shows that this is a weak acid. Okay, now let's move up to a quantitative assessment of quantitative evaluation of this solution. Calculate the pH of a 0.25 molarity solution of this methanoic acid. Ka value is given right there. Okay, so in this case, we need to set up an ice table. Setting up an ice table is very important skill. So let's learn how to do it properly. So we have an ice table. Let me write this one as HA, monoprotic acid, and this one as conjugate base A negative, and then hydronium ion. So then the equation is the acid is deprotonated in water, producing its conjugate base A negative plus hydronium ion. So this one is the equation. Let me write initial concentration, change in concentration at equilibrium ice table. Initially we have 0.25 molarity of acid. Water is a solvent, its concentration does not appear, so let's skip representing the concentration of water. Initially, hydronium, the conjugate base, we have not added anything of this one. Initially, the water hydronium concentration is small. Initially in pure water is 1.0 times 10 to the negative 7 molarity, but that amount is much smaller than the amount of conjugate base produced from this dissociation of acid. So then we cannot safely assume that initial amount is close to zero. Okay, and then about X molarity of small amount of this acid is dissociating and decreased. As a result, the conjugate base and hydronium ion concentration increasing because it is one-to-one reaction. So at the end, when the equilibrium is established, in fact, for acid-base reaction, it is a very fast reaction. Equilibrium is fastly achieved. This one is out of initially 0.25 molarity, X by X molarity has decreased, and conjugate base and hydronium ion, it is X and X. So let's write Ka expression. Ka is Ha, the acid concentration under conjugate base and hydronium ion concentration. At which stage? Yes, at equilibrium stage. So we are looking at this value, equilibrium value, this value. So let's plug in this value into this expression. So let's plug in those values into this expression. So Ka value is equal to X times X divided by 0.25 minus X. Okay, in this case, we need to solve this equation. Ka value is 1.8 times 10 to the negative 4. Plug in this value into Ka. We need to solve it. When you solve this equation as it is, it will be leading up to the formation of a quadratic equation, and we need to use quadratic formula to calculate the value of X, which takes time. In many of the cases of weak acid, and we can do approximation, the value of X is much smaller than 0.25. So we can assume that X is much smaller than 0.25 molarity. Based upon this assumption, we can simplify. 0.25 minus X is approximately equal to 0.5. And we'll be verifying this assumption. Okay, then Ka expression is much more simplified. It is now X squared divided by 0.25 minus X. The denominator is simplified. It is simply 0.25, and it is equal to, let's plug in the Ka value, 1.8 times 10 to the negative 4. Here now X squared is equal to 0.25 times 1.8 times 10 to the negative 4. X is equal to square root of those values, which is 6.7 times 10 to the negative 4 molarity. Okay, let's check our assumption is valid or not. So X over 0.25 times 100%. 6.7 times 10 to the negative 3. So this value is 10 to the negative 3 over 0.25 times 100. Then I find this one is 2.7%. 2.7% is less than 5%. Our criteria to determine if X is smaller than, significantly smaller than the, significance of X value, smaller than, much smaller or negligible compared to 0.5 is 5% rule. Because this is 5%, our assumption is valid. Okay, and then it is asking finally what is the pH value. pH is negative, definition negative of hydronium ion concentration. So then hydronium ion concentration, as you see in here, this one is an X. So let's plug in X value to hydronium ion concentration and let's calculate it. So it is negative log of 6.7 times 10 to the negative 3. It is 2.17. 2.17. So let's write the, usually it is good to remember to write the pH value with 2 decimal places. pKa, pH, those p values, let's write with 2 decimal places. Let's evaluate the situation. 2.17. This one is getting closer to strongly acidic condition. 2.17. Why this one is close to 2.17? Usually pH of of those like carboxylic acid solution is now 3.45, close to the pKa value. There are two things. First, the pKa value, Ka value is relatively large, 1.8 times 10 to the negative 4. This one is relatively large. Forming acid, this methanoic acid is acidic, compared to more acidic than other regular carboxylic acids, and also the concentration of 0.25 molarity. Usually working concentration 0.1, 0.2 molarity. 0.25 is a little bit higher than the usual concentration. These two factors combine to make the pH value 2.17. Okay, now let's move up to the next one. Draw the Lewis structure of this methanoic acid. This is Lewis structure, and make sure that you understand the structure of carboxylic acid. Very important. This part, carboxylic acid, COOH. So COOH. And because oxygen needs to satisfy the octet, and each of the oxygen has two lone pairs. Okay, and then let's move up to the next one. Mixture of 50 ml, 0.25 molarity of hydrazine. NH2NH2 is a reactive chemical species called hydrazine. And 50 ml, same volume, same concentration of formic acid. Its Ka and Kb value, because hydrazine contains nitrogen with lone pair, this is a weak base. So this one is gaining proton from water, making the proton, the conjugate acid of this hydrazine. And Kb value is 1.3 times 10 to the negative 6. Now we are mixing them up, these two solutions, same volume, same concentration. And let's write acid-base reaction. So this methanoic acid is acid. It will be giving out proton. The hydrogen, this hydrogen is protonated. Should be deprotonated. It will be giving out to the weak base, hydrazine. And then it'll be very small portion will be deprotonated because both of them weak acid, weak base. And it will be forming formate ion, methanoate ion plus this conjugate base of hydrazine. Okay. Now the resulting solution acid basic was neutral. Now let's look at its Ka value and Kb value. 10 to the negative 4, 10 to the negative 6. 10 to the negative 4 is about 2 orders larger. So Ka is more effective. So then the solution will be an acidic solution. When you are mixing acid and base together, look at their Ka value. In this case, mixture of weak acid, weak base, everything else is same. The volume is same, the concentration is same. So then its concentration is the resulting solution. The acidity will be determined by its Ka value, Kb value comparison. Now, like free response problem of AP chemistry is really combination of many problems, many concepts. This is not an exception. So now let's combine this one with the concept of oxidation reduction reactions. So by adding a catalyst, many times we have metal catalyst working or other catalysts, and then this one is decomposing. Methanoic acid is decomposing into carbon dioxide and hydrogen gas. Is a reaction or redox reaction justify your answer? So now let's assign the oxidation number. So hydrogen is always +1, almost always +1 in a compound. Oxygen is -2. And when you assign the oxidation number of hydrogen now +3, right? Let me see. +2. Let me correct it. +2, because it is right next to it. 1 hydrogen and then two oxygens. So when you add up all the oxygen number, it should be 0. And let's look at the carbon. Here is +4 because the oxygen is -2. And then when you add up everything, it'll be 0. and hydrogen is 0 because it's element. So when you compare carbon, carbon plus 2 to plus 4. So this one is oxidation. We can see this one in two respects. First, definitely oxidation number, oxidation state increases. Oxidation state of carbon increases. So this is definitely oxidation. Second, then the number of hydrogens, number of carbons, number of oxygens doesn't change, but number of hydrogens, number of hydrogen atoms decreased. Hydrogen atoms decreased. So I wanna two of them has left the structure. I wanna remind you. Let's be reminded that the hydrogen has the smallest electronegativity. So when it is binding, has covalent bonding with carbon, it is always +1. But in this case, it is lost, meaning it has left the structure, meaning carbon has lost its electron density, so carbon is not oxidized. And oxidation reduction reaction always occur as a pair. Then this hydrogen is from +1 to 0. So this is a reduction. Initially, hydrogen has lost its electron density. It was bearing a partial positive charge. Now it is 0. So this is reduction. Okay, so then remember these two criteria. Oxidation is oxidation state or oxidation number increasing or number of hydrogen atoms decreasing. This is oxidation. The opposite is reduction. Now let's combine this one with gas evolution reaction. This is definitely gas evolution reaction. Both of carbon dioxide and hydrogen gas is gas. So as the reaction progresses, as the reaction time goes, and then the pressure is increasing as you see here. And total pressure when the reaction goes to complete, this one is 24 atmospheric pressure. And the rigid wall of the container, the volume is measured to be 4.3 liters, temperature is 25 degrees C, pressure is given in the graph. Calculate the number of moles of CO2 gas produced in the reaction. So we need to have a two-step approach. First step, definitely we need to have total number of gas particles. This is coming from ideal gas law. So P total V divided by RT. When we rearrange the ideal gas law, number of moles of gas is PV over RT. So now we know that total volume is 24 atm. Total pressure in the graph right there, 24 atm, and volume is given 4.3 liters. And R is a constant, 0.08206 liter atm per mole K. And then times temperature, 25 degrees C. Remember, temperature must be always Kelvin unit in order to use the ideal gas law. So let's add 273.15 to make into Kelvin unit. Okay, now let's calculate it. The value is 4.22 moles. So atm cancels out, liter cancels out. Here this is Kelvin. Kelvin cancels out. 1 over 1 over mole. The unit is now 4.22 mole. Now once you calculate the total number of moles of gases, let's move to step 2. Find out number of moles of CO2 gas. CO2 gas. So this is a mixture. And then CO2 gas is related with total moles, number of moles of gases times mole fraction. Okay, so in this case, from 1 mole decomposition of the methanoic acid produces 1 mole of carbon dioxide and 1 mole of hydrogen gas from the equilibrium, from the balanced chemical equation. Then mole fraction is 1 over 2. Because 1 mole, both of them generate the same mole number. So it is now 1.2 times 4.22 mole. Answer is 2.11 mole. When you consider sigfix, the final answer 2.1 mole. Okay, so this problem is, I really see this pattern, combination of a gas law with the acid-base concept. We saw this one previously, recently in also examples this type of problems. 2023, so this one 2023 free response problem number 5 also is making combination of acid-base reaction with the gas, either gas law, gas laws. Okay, so then let's be prepared to do similar calculations. Okay, now let's see conceptual understanding of a catalyst. After the reaction has proceeded for several minutes, does the amount of catalyst increase, decrease, or remain the same? So what is a catalyst? Catalyst is getting involved in a chemical reaction, and it is reducing, or it will be decreasing the activation energy. It will be providing another reaction route, and with the smaller activation energy. Let me draw a concept here. We have x-axis now reaction progress, and y-axis is now potential energy. And without catalyst, the reaction has high activation energy, right there. High activation energy. Now, when you have a catalyst, and then it will go through another reaction route, and activation energy now becoming much smaller right there. So this one is activation energy. So it is providing another reaction route with smaller activation energy, so then reaction goes faster. But catalyst is not consumed. It is getting involved in a chemical reaction, but it is regenerated at the end. So the total amount of catalyst is not reduced. So it is remaining the same. And when you go to upper division of chemistry, we learned the case of catalyst poisoning. Actually, the reality is always deviating from our theoretical concentration or concept. So actually, as the reaction goes, the catalyst is not poisoned and its efficiency is decreasing. But this is for upper division concept. For our level in general chemistry, we can safely assume that catalyst is remaining the same always. Okay, in this problem, we were combining the concept of acid-base, especially how to deal with the acid equilibrium, acid dissociation constant Ka, the definition, how to calculate the pH, assumption that, assumption that the change X is much smaller, less than 5% of initial value, and checking the validity of our assumption and drawing the loose structure and acid-base reaction, and also finally combination with redox reaction and gas evolution reactions. Okay, this concept is important one, so let's have a good understanding of this type of problems. Okay, I'll see you in next video. Thank you.